Jai Hind, dear students. Myself Alok Kumar. I am the assistant professor in EC department, AKGEC, and today we will take the topic from the subject electronic devices, and we will take two topics. First is the Fermi level, and second is the Schrodinger wave equation. So first we will see the derivations and the meaning of this Fermi level. For different type of semiconductor, like in intrinsic semiconductor, in extrinsic semiconductor, and type or p-type semiconductor. So first we will discuss this, and then we will discuss the one topic from the quantum mechanics, that is Schrodinger wave equation, right. So first, if I start with Fermi level. So how we can define the Fermi level, right. So basically Fermi level tells us the probability of finding the electron in the semiconductor. Like, so if we have a structure like this, so we can draw the energy band diagram. Suppose this is the energy band diagram, and here we have the lowest energy of the conduction band is EC, and the highest energy of the valence band is suppose EV, and the difference between these two energy levels is EG, which is called forbidden energy gap, right. So if you want to find out the probability that whether electron is in conduction band, whether it is in valence band, or it is somewhere else, so we can use this concept of Fermi level, right. So this is basically the probability which tells us the existence of electron in we can say at different energy levels, right. So to find this probability, we can use the this formula. This is the Fermi direct distribution function. This is Fermi direct distribution function, Fermi direct distribution function, and it can be given as Fe is equal to F, that is a function of this energy, right. So 1 upon 1 plus e to the power E minus EF upon kT, right. So using this formula, we can find the energy of the electron, right. So here in this formula, this is the probability, and here E is the energy of electron for which we want to find out the probability, and EF is the Fermi energy, and K we know the Boltzmann constant, and T is the temperature in Kelvin, right. So if I consider that at T is equal to 0 Kelvin, if I want to find out the probability at T is equal to 0 Kelvin, and if I take the first case when E is greater than EF, we want to find out this probability, that what is the probability with this case E is greater than EF. So in this case, Fe will be is equal to 1 upon 1 plus. So here we are considering E, that is energy of electron, is very greater than energy of Fermi level, right. So Fermi energy. So E is greater than EF. So here if I consider here T is 0, so this will be e to the power infinity. This term will be e to the power infinity, right. And e to the power infinity, we can write 1 upon 1 plus e to the power infinity, we can write it will be infinity, or the final value will be 0. So the condition for this or the probability for this, that any electron which can have the energy more than the Fermi level, the probability for this condition is 0% only, right. So there will be no electron which will lie above the Fermi level, okay, at 0 Kelvin. Okay. Now second case, if I take second case, that is energy of electron is less than the Fermi energy. Let's discuss this case. So here we are taking electron of energy is less than the Fermi energy. What is the probability of this condition, right? So again we can find out the Fe will be is equal to 1 upon 1 plus. Now here E is less than EF, so it will be e to the power minus infinity, and e to the power minus infinity will be is equal to 0. So 1 upon 1 plus 0, it will be is equal to 1, or we can say 100% probability. There is 100% chances that any electron at 0 Kelvin will have the energy lowest, lower the Fermi energy, right. So with Fermi level, we can say it is just the probability by which we can find the existence of electron, okay. Now in different type of semiconductors, like in intrinsic semiconductor, in n-type semiconductor, or in p-type semiconductor, these Fermi levels lie at different levels. So for example, if we discuss one by one, so first case we can take for intrinsic semiconductor. intrinsic semiconductor, right? So in intrinsic semiconductor, if we want to draw the energy band diagram, so how it will how we can draw. So here we have this lowest energy of conduction band EC, here we have EV, right, and this is our forbidden energy gap EG, and in intrinsic semiconductor this Fermi level will lie in the middle of this energy band gap, right. So here it will be the Fermi level EF. It will be the Fermi energy EF, right. Now this energy will be Eg by 2, and similarly this energy will be Eg by 2 as this Fermi level is lying, as this Fermi level is lying in the middle of the energy band gap, right. So now if we want to prove this, that how we can prove that this Fermi level will lie in the middle of the energy band gap. So for this we know that in intrinsic semiconductor, number of electrons will be is equal to number of holes, or in symbolic representation we can say n will be is equal to p, right. Now we also know the concentration of electrons can be given as n will be nc e to the power minus ec minus ef upon kT, and the concentration of holes can be given as nv e to the power minus ef minus ev upon kT, right. So now if we rearrange these terms, so we can have nc upon nv, and it will be is equal to e to the power minus ef minus ev upon kT divided by e to the power minus ec minus ef upon kT, right. Now again we can simplify it, and we can write it as nc upon nv, and it will be is equal to e to the power minus ef plus ev plus ec and minus ef upon kT, right. Again we can further simplify it, and we can write it as ec plus ev minus 2 ef upon kT, right. So this is nc upon nv. Now if I take the natural log of both sides, then we can again rewrite it as, we can write it as ln nc upon nv, and it will be is equal to ec plus ev minus 2 ef divided by kT, or we can write it as ec plus ev minus 2 ef is equal to kT ln nc upon nv. Finally we can find the value of this ef, right. So here ef will be is equal to ec plus ev divided by 2 plus kT ln nv upon nc, right. So this will be the final formula. Now what are these nc and nv? Basically nv is the energy density states in valence band, and nc is the energy density states in conduction band, and if I consider that if Nc is equal to Nv, so how can I write this equation? This will be EF is equal to EC plus EV divided by 2, right? Or this equation can be written as EF is equal to EG divided by 2. So this is the proof that in intrinsic semiconductor the Fermi level will lie in the middle of energy band gap, right? So by this way we can prove this. Now next case we will take of n-type semiconductor, right? In n-type semiconductor where the Fermi level will lie. In n-type semiconductor. So after doping the intrinsic semiconductor, when we dope the pentavalent impurity, right? So we can make the n-type semiconductor, and after doping the Fermi level will shift. As we know, in intrinsic semiconductor the Fermi level will lie in the middle of energy band gap, and after doping it will shift. In n-type semiconductor it will shift towards the conduction band, right? So again we can draw the energy band diagram. We can draw the energy band diagram, and here we can say it is EC, EV, and this is your forbidden energy gap EG, right? And in n-type semiconductor Fermi level will lie near this conduction band. Here this Fermi level will shift. In intrinsic semiconductor we know the Fermi level was in the middle of this energy band gap. Here we can say it was EI. For intrinsic semiconductor we can say, or we can say EFI, right? So for intrinsic semiconductor it is in the middle of this energy band gap, and for n-type semiconductor after doping it is shifting towards the conduction band. So now we want to find out that how much is this gap, right? So and how we can prove that the Fermi level will shift towards the conduction band, right? So we will do it through a derivation. So as we know, the concentration of electrons N can be given as Nc e to the power minus EC minus EF upon kT, right? So this is the concentration of electrons. Okay, now this n, this small n, we can use the relation that is for n-type semiconductor. We can write Nn into Pn will be is equal to Ni square, right? Nn into Pn is equal to Ni square, and here this Nn is the concentration of majority charge carriers in n-type semiconductor. And as we know that in n-type semiconductor these majority charge carriers are mainly contributed by the pentavalent doping or pentavalent dopants, right? So this Nn will be approximately is equal to Nd. That is the concentration of donor atoms, right? So due to this these electrons are the majority charge carrier, right? So this Nn can be written in terms of Nd. So here we can write Nd is equal to Nc e to the power minus EC minus EF upon kT, right? Now we can again rearrange the terms. So Nd upon Nc, it will be is equal to e to the power minus EC minus EF upon kT. Again we can take the natural log, and we can write it as ln Nd upon Nc, and it will be is equal to EC or minus EC plus EF upon kT. After taking natural log we can write it. Again we can rearrange the terms. So EF will be is equal to EC plus kT ln Nd upon Nc, or this equation can be written as EF is equal to EC minus KT ln NC upon ND. So this will be the final value of the Fermi level in n-type semiconductor, right. So here we can see the Fermi level in n-type semiconductor is just below the conduction band, and what is this, what is the value of this energy? This energy is KT ln NC upon ND. So here NC, we know NC is the energy density states in conduction band, and ND is the concentration of donor atoms, right. So this is the way we can find the Fermi level in case of n-type semiconductor, right. Similarly, we can do this for the p-type semiconductor also. So next is the Fermi level in p-type semiconductor. In p-type semiconductor. So when we try to dope a intrinsic semiconductor with trivalent impurity, like boron, aluminum. So when we dope these impurities into the intrinsic semiconductor, then we will get the p-type semiconductor, right. And in p-type semiconductor, the Fermi level will move towards the valence band, right. In intrinsic semiconductor, Fermi level is in the middle of the energy band gap, and in p-type semiconductor it will move towards the valence band, right. So through the energy band diagram, how we can show this? So here suppose this is EC, EV, energy of valence band. Here we have this forbidden energy gap EG, right, and Fermi level will lie somewhere here. So this will be EF, and EI we know it is in the middle of the energy band gap. For intrinsic semiconductor, the Fermi level lie in the middle of the energy band gap. Again, we can write it as EFI. Clear? Now we know the concentration of concentration of holes, because it's a p-type semiconductor. So here we should take the concentration of holes, not the concentration of electrons, because in p-type semiconductor the holes will be the majority charge carriers, right. So if we take the concentration of these holes, so it can be given as, so we are talking about p-type semiconductor, concentration of holes in p-type semiconductor. So we can write in as Pp. So Pp will be is equal to Nv e to the power minus EF minus EV upon KT, right. So this is the concentration of holes. Again, this Pp can be written in the form of Na. This Pp will be approximately is equal to Na. Why? Because what is Na? Na is the concentration of acceptor atoms, right, or acceptor atoms. So these acceptor atoms are responsible to make holes the majority charge carrier in the p-type semiconductor, right. So that's why we are writing Pp will be is equal to Na, or this relation can be proved by using the law of charge neutrality, right. What is the law of charge neutrality? As we know that according to this law of charge neutrality, that the material will be neutral, right. That is, the total negative charge will be is equal to the total positive charge, right. So if I write the total positive charge and total negative charge, so total positive charge will be P plus Nd, and total negative charge will be N plus Na. So this is the equation that we get from the charge of law of charge neutrality, right. So here if I talk about the p-type semiconductor, right, in p-type semiconductor, for p-type semiconductor I can write it as Pp plus Nd is equal to Np plus Na. But in p-type semiconductor, what type of doping we use? We generally do the acceptor, we generally dope the acceptor atoms. So here Nd will be 0, this term will be 0. So Pp will be is equal to Np plus Na, right. Here Pp is the concentration of holes in p-type, so we can say these are the majority charge carriers. Np is the concentration of electrons in p-type, that is, we can say these are the minority charge carriers, and Na, these are the we can say dopant atoms, right. So the concentration of this Np will be very, very less than as compared to Na, because these are the minority charge carriers. So this equation can be written as Pp will be approximately is equal to Na. So this is the law of electrical neutrality, and using this law we can write here Pp is approximately is equal to Na, right. So this equation will be Na is equal to Nv e to the power minus Ef minus Ev upon Kt. Okay. Now we can write it as Na upon Nv, and it will be is equal to e to the power minus Ef minus Ev upon Kt, right. Now we can take the natural log, and it will be ln Na upon Nv, and here we can write minus Ef plus Ev upon Kt, or we can find this Ef. So Ef will be is equal to Ef will be is equal to Ev plus Kt ln Na upon Nv, or it can also be written as Ef is equal to Ev minus Kt ln oh, no need to write this. Okay, so only this will be the final value. So Fermi level will lie just above the valence band, and we can give the amount of energy that will be the difference between the Fermi level and the valence band. So that difference of energy can be given using this term. So Kt ln Na upon Nv will show the difference of energy between the Fermi energy and the valence band energy, right. So this is the way how we can prove or we can find the Fermi levels or energy of the Fermi level in different type of semiconductors. In intrinsic semiconductor we have solved, in n-type semiconductor, and then in p-type semiconductor, right. So now next topic is we will take from the quantum mechanics, that is the Schrodinger wave equation, right. So in quantum mechanics, as we know, the laws of classical physics, they don't work here in quantum mechanics. So to find the behavior, or to study the behavior of the electrons or small particles, generally we use quantum mechanics. And after de Broglie theory, when after de Broglie hypothesis, when he say that electron or the small charge particles may also have the dual property, they may behave like a particle and then they may behave like a wave also. So after this the Schrodinger wave equation comes, and it will show the behavior of the charged particle, small particles, or we can say the electrons. So we can, using this Schrodinger wave equation, we can find the energy, we can find the position in different directions, right. So we will discuss the Schrodinger wave equation, or we will derive it for in two cases. One is time dependent and one is time independent. So first we will take the time independent case, right. So Schrodinger wave equation, Schrodinger wave equation we are discussing, and first case we are taking the time independent case. Time independent Schrodinger wave equation, right. Time independent Schrodinger wave equation. So we will start with the wave function. So as we know, wave function can be written as psi is equal to e to the power I kx minus omega t, right. So this is the wave function, and it can be written as psi is equal to e to the power I kx minus omega t, right. So here k, what is k? K is the wave vector. This k is the wave vector, and it can be written as k is equal to 2 pi upon lambda. Here k is the wave vector, and k can be written as k is equal to 2 pi upon lambda. Here lambda is the de Broglie wavelength, right? And one more term, that is omega. This omega is nothing but we can write it as 2 pi into nu. Here nu is the frequency, and nu we know the relation that energy can be written as E is equal to h nu. So from here we can say nu will be is equal to E upon h, right? So if I put this value here, so it will be omega is equal to 2 pi E upon h, 2 pi E upon h, right? Again, this h is Planck's constant, and we know this h can also be written as 2 pi h cross or h bar. This is h bar is the reduced Planck's constant, and this h is the Planck's constant, right? So here if I use this relationship, so we can write it as omega is equal to 2 pi E divided by 2 pi h bar or h cross. So this 2 pi will be cancelled out by this, and final value will be E upon h cross, right? So omega we can write it as omega will be is equal to E upon h cross, right? Similarly with this k we are saying it's a wave vector, and it can be written as k is equal to 2 pi upon lambda. Here lambda is the de Broglie wavelength, and we also know that p is equal to h upon lambda. This relation we also know, right? So from here we can write lambda will be is equal to h upon p. Okay, so here if I put this value, so k will be is equal to 2 pi upon h or p, again 2 pi p upon value of this h, Planck's constant, we can write in terms of the reduced Planck's constant, and we can write it as 2 pi h cross. Here it will be cancelled out, and finally we can write k is equal to p upon h cross, or p upon h cross. Here in this way we can write k is equal to p upon h cross. So with these two relationships, that is k, we have proved k is equal to p upon, we can write p upon h cross, and omega we can write E upon h cross. With these two relationships we will start proving the Schrodinger wave equation, right, time independent. So we have psi is equal to e to the power I kx minus omega t. So if I differentiate this equation with respect to x, right, so if I write d psi by dx, so it will be is equal to, from here we will get I into k into e to the power I kx minus omega t, right? If I further differentiate this, what will I get? We will get d square psi over dx square, and it will be is equal to I k square e to the power I kx minus omega t, right? Now if I simplify it, so d square psi over dx square, it will be is equal to I square will be minus 1, so it will be minus k square, and this term we can write in terms of psi. So this will be psi minus k square psi, right? Now this k we have already solved, k is equal to p upon h cross. So here I can write that value. So it will be minus p square upon h cross square into psi, or we can write it as h cross square d square psi over dx square, it will be is equal to minus p square psi, or p square psi will be is equal to minus h cross square d square psi over dx square, right? So this is the equation that we will use in next steps, right? Now we know that the total energy, according to the law of conservation of energy, we can write the total energy can be written as the kinetic energy plus the potential energy. This will be the total energy, right? And this kinetic energy will be half mv square plus potential energy will be Vx, right? Now if I multiply here m, so here in numerator it will be m square v square, and in denominator it will be 2m. After multiplying with m, so we can write it as this. We know p is equal to mv, so here p square will be is equal to m square v square. So m square v square can be replaced by this p square. So total energy, that is we can say E can be given as p square upon 2m plus Vx, right? Now if I multiply with psi, so E psi will be is equal to p square psi upon 2m plus Vx, and this p square psi we have already calculated. It is equal to minus h cross square d square psi over dx square, right? So we can put this value. So it will be E psi is equal to minus h cross square d square psi over dx square, and it will be 2m as it is plus Vx. I think here we should multiply with psi also, right? So this will be the equation. Now we can simplify this, and we can write it as E psi plus h cross square upon 2m d square psi over dx square minus Vx is equal to 0, right? Now if I multiply this equation by 2m upon h cross square, multiply this equation by 2m upon h cross square, so we can write it as 2m upon h cross square into E psi plus d square psi over dx square minus Vx into 2m upon h cross square is equal to 0. Again we have to put psi here also, right? Now after rewriting this, so we will get d square psi over dx square plus 2m upon h cross square, we can take common, and E psi minus Vx psi will be is equal to 0. Further we can write d square psi over dx square plus 2m upon, we know this h cross the actual Planck's constant can be written as 2 pi h cross, and this h cross we can calculate, it will be h upon 2 pi. So here h cross can be written in terms of this h, and it will be h square upon 4 pi square, right, into E psi minus Vx psi is equal to 0. After simplifying this, we will get d square psi over dx square plus 8 pi square m upon h square into E minus Vx into psi is equal to 0. So this is one dimensional time independent Schrodinger wave equation. In all three dimensions, we can write it as d square psi over dx square plus d square psi over dy square plus d square psi over dz square plus 8 pi square m upon h square into E minus Vx into psi is equal to 0. So this will be the, we can say, the final Schrodinger wave equation in time independent form, right? Again, we can replace this with delta, which is del operator. So this can be replaced with del square. This term can be replaced with del square, and the final term we can write del square plus 8 pi square m upon h square into E minus Vx into psi is equal to 0, right? So this will be the final term, we can say, or we can say this is the three-dimensional form, this is in one-dimensional form, right? So here we stops. Thank you.